So the first thing that we'll talk about for our component drawing is to learn a little bit about a check assembly. A check is a check valve. It lets water flow one way and keeps it from flowing the other way in a pipe. And so this piece here would screw into a device. And then this piece is the clapper, and it opens up and closes. It opens up when water wants to flow in the upward direction, and it closes up when pressure comes and pushes on the back. Now, this particular one, it's not shown. There's lots of other parts that go on this. There's a spring and a cam bar and a roller and a rod and spacers and all sorts of stuff. But this will give you the main idea of it. So when the water pressure is higher on this side than on this side, this will open up. And let the water start flowing through. And then when the water wants to stop flowing, it closes back down. And you would think that that would be a very simple thing, but the constraints on this particular set of parts was incredibly tight. And this was a product that I did work with. And there was a lot of work that went into making this work efficiently and effectively and make it so that we could produce it at a reasonable cost. And it turns out that it worked better, more effectively, and more efficiently than any other device that was available in the field at that time. So we were very successful with it. Okay, so we're going to look at the drawings required to make this part and the drawings to make this part. This part here, the swing check, is called a clapper. And this one here is called a seat ring. And then whenever you screw something into a pipe, it usually needs something to seal. So I showed the O-ring also. And we'll talk about all of those things. So that's the start of what we've got to look at. So now let's take a look and see how this part gets made. Okay. First, there's a part that is purchased. Okay. And it's called a vulcanized part or a blank. And this part here that you're seeing that's green, that's made out of Noril GTX. It's an automotive plastic. It's very strong and very stable. And then on the bottom, there's a little segment of it that is EPDM. That's a type of rubber product. So this is very stiff and strong. And there's a rubber product on the face that will seal against the seat ring. Okay, now to make those parts stick, there's a process called vulcanization. When you vulcanize something, basically you heat the rubber up and fuse it to the hard part that it's going to connect to. And then it's really on there. It really, really goes together molecularly. And so this is a vulcanized part. And we happen to use the same company to do both things. They made a molded plastic. It's called injection molding. A molded plastic part that looked like this. Mostly. There were other holes to make it lighter that I'm not concerned with for our project. But these were all the functional features. And then they had a shop that would vulcanize it. So with one purchase order, we could send a drawing of this vulcanized part and the company would make it for us. And we would send a drawing with it that showed all the important dimensions that we were interested in. And so your job, I've got this for you. So your job is going to be to take this clapper and dimension the vulcanized part so that you could send it to a factory to be made for you. Okay? Once that's done, then we need to make it so that all the holes that we're going to connect things up with fit and that everything is all correct. And so let's go ahead and open that one up. That's in my clapper machined. So once we get the part, then we're going to machine the part. We're going to stick it on a lathe or a mill or a grinder or a drill press or some combination of those things. And we're going to put in all the holes that are needed and machine surfaces flat where they're needed, and add little features that are needed. That was an afterthought, or we would have had it molded in, but we found out we needed that later on. Oops, and I see I've got a little bit of a problem here. I moved this. Need to move that up a little bit. I moved some stuff, and obviously it didn't go. So I'll fix this up a little bit for us so that we have a better drawing to work with. I'll get that one fixed up for us. Okay, before we get into the major part of that, see if I can edit that sketch. Move that to where it belongs. Goes right there. There we go. Now we've got it. Okay, and so we've got all of these things to think about as we work through it, and it's important to understand the design and how it works. So the first thing that we would have to know is, if we go back to this, you see that this has to sit flat. And when we look at it this way, it's impinging in here. Okay, there's a seat here, so let me go ahead and see how it's got to come down. Right about there, it starts to seal, and this hard part penetrates the EPDM. And this angle where it starts to do that is super critical to how well this works. And so this was very critical that we control the dimension between this pivot hole and this surface right here. So there's a grinding operation. You can see that's where the EPDM was. And then we grind this flat so that this happens to hit at just the right angle. And you don't have to go into why that happened, but it did. It was very, very critical. Okay, so from the flat EPDM, we have to machine this off. And that has to be nice and flat as it goes. Okay, and so there's a very strong relationship between this point and this point. And you don't see it, but there's a bar that goes across. There's a roller sitting in this little pocket right here in this pinhole. And that has to be absolutely just right also, or the forces don't work out. This is a very complex set of forces that allow this to open up freely and not have a lot of resistive force in it. So the other thing that's very important is the relationship between this hole and this hole. And then it turns out that there's a flat area on the front of this, because when I first got this part, this was all round, and I found out that it was possible with all of the tolerances, with this as big as it could be, and that hole as far forward as it could be, and this hole as far forward as it could be, and a spring on here, that it was possible for this part to rub against the spring holder, and that made it fail. So we cut this back, and that became our defining point. So we define it by that bottom surface, this flat surface, and all of the holes are relative to those. Now it's hard to line up everything to a flat rubber surface, so we chose the back hard surface to be our primary point. And then we found a machining process where we could control that rubber. If we froze this part and ground this rubber, then we got an excellent flat surface that we could then set up on and put these holes in where they belonged. So it's a very tricky part, and it's got a lot to it. But the main thing is we're going to buy this blank, and then we're going to machine this surface right here that says EPDM, and then we're going to set that EPDM up against a little fixture, and then shove it against here and clamp it in place, and then put in this hole and this hole. And we're going to tell the machinists, even if it's done by CNC, we're going to tell the machinists and the inspectors exactly how all that has to fit together. So that's what we're going to do with the clapper. Okay, so let's take a look at some parts again. And so you see there are some dimensions on the machined part that have parentheses around them. That means that we're noting that dimension, but that it's already been made. It's a reference that has already been made, and so the machinist doesn't really have to worry about it. Okay, that's what it's a reference dimension. It's already there. So there are a few. There's this outside diameter and this overall length. Okay, so those are already there because we bought the part. And now we're going to machine it. We don't have anything here because that's on the bought part also. But what we do have to machine is this hole and this part of this pocket. Okay, so right here, we show how to put this little radius in. And that's going to be done with a mill. It's going to come down, and then by CNC, it's going to run that little shape and cut that little groove. There's the width of the groove, which I think I show somewhere else. I hope I show it somewhere else. It looks like I need to put that dimension on there. Okay, I'll put that. See, you can always find stuff that got left off. Okay, so I have to find that dimension. Let me do it right now. So let me put a center mark on that. And we always go from a center mark to an edge. And then from the edge to the edge. And that's just a standard that we use. I'm going to move this over a little bit. And I'm going to move this over a little. All right, now I can get that to move. Sometimes I just go and do it again. There we go. So now we've got that dimension. So I'm going to take a tool bit that's 20 thousandths wide and a mill and just run it down that little pocket. Okay, and there's a radius that's allowed on there. Okay, it says it in the notes. So that's how I have to make that little pocket. Now this view over here tells me all about how to put this hole in. That's feature number H2. This A means that that's where I need to measure everything from. So when I set up, I'm going to set up off of that surface to get certain measurements when I do my measuring. Okay? But I've got some other things to look at too. Okay, so there we go. So I've got that. And I've got that one over there. They're all from that back surface. And that's my A surface. And you can see it's got a very tight tolerance. And then you're going to see this weird set of symbols that we have to talk about in a moment. But all my measurements are based against my hard back surface, and I measure down and I measure over from that flat to find that position. Okay? And this is a little bit interesting. We'll talk about that in a little bit. But there's one, and then there's another one here, feature H1, hole number 1. And again, I measure its position and I put it into place. Okay, and here we go. Here's this, R1. Okay, and I'm going to hold against that as I make my part. And then I show where I go to get that machined surface. Okay, and that becomes my number B. And this says it has to be parallel within 2/1000ths of my A back surface. So that's kind of cool. That means wherever I measure between here and that surface, every measurement has to be within 2/1000ths of the same thing. And it also has to be flat within 2. Okay, so that's 2 different things. So this surface has to be flat and it has to be parallel to this. And you can understand why, because I'm really looking at this as being my controlling point. But since it's rubber, I want to take my dimensions off of something hard. Okay, but I do have a note about this. Now this has got parentheses around it because I've already said that this is A. So I put parentheses. I've already said it somewhere. Okay, let's take a look at this one now. Okay, 0.234 plus 10,000, so it can be a little bit farther away, but it can't be any closer than 0.234. And we found that out by doing tolerance reviews and trial and error. We just found out that we had to really control where this position was for the forces to work right and for the interference to work right. Okay, so remember that when we do mechanical dimensioning, every single dimension needs a tolerance. If you have a dimension without a tolerance, you have to go read the tolerance down here. So this one says 0.220. So it says that one can be either plus or minus 10,000ths of an inch. 0.210 to 0.230. But this one was special. 0.234 to 0.244. If I measure anything other than that, my part is no good. And look at this hole diameter. 0.187 plus or minus 1/1000th of an inch. That's because there was a pin that is a press fit into this part. And so we wanted to make sure it would always press in. Okay? And that it didn't go too hard. So that's a typical press fit. So that tells you a little bit about this. Now let's take a look at this. True position means that anywhere I look at this hole, not just on the surface, but all the way along the hole, all the way from this little point to the one on the other side, all the way through, wherever I measured that center line of that hole, it has to be the same no matter what when I measure it from here to here, that's my C, and from here to here. Every time I measure it. Now it tells me that I can have a little bit of a wide range. So if I measured one of them at 0.236 everything has to be within 2 thousandths of 0.236. If I measure one at 2.240, everything has to be within 2 thousandths of an inch of 0.240. So this gives me a little bit of latitude of what it is, but this has to be lined up really, really, really lined up with this surface and this surface. And that was just the reality of making this part work. We don't like to create things that are so hard to make, but sometimes it has to be done to ensure that the part works. Now, this part happens to be certified for a backflow preventer, which keeps potable water safe in the public system. We're talking about public safety here. We are not allowed to have a part that doesn't work. It's not just an inconvenience, it's public safety. So it was worth it to us to go ahead and find out what it really took to make this always, always work, no matter what all the other parts were built at and everything. So we've done that here. And you can see that on this one too. This one, of course, says, oh, look, I've got a lot of ability to make my part from 1 inch to 1.01 inches. Okay, you can see that from this tolerance here. But it's got to be parallel. I can't have 1 here and 1.01 here. No matter what I measure, every measurement I ever take along this whole surface has to be the same within 2 thousandths of an inch. So I lay this on its back on A, and then I measure the height of this surface, and no matter where I measure it, it has to be the same within 2 thousandths of an inch. And of course, that means also that I've got to be flat within 2 thousandths of an inch. Okay, so this part could bow a little bit, and I wouldn't pick it up without this. Okay, so that tells us about this hole and this surface. Let's go take a look at another one. This one back here is the same thing. I have a dimension that's plus or minus 5, but it's got to be true position. Whatever I measure it at has to be the same no matter all along that hole, from one side of the hole to the other side of the hole. I have to measure it the same within 2 thousandths of an inch. These are called geometric tolerances. These are called dimensional tolerances. You need both sometimes to fully control the dimensions of a part. Okay, now this one has a little bit more room on it because it's a sliding fit, but it can't be a loose sliding fit. It's got to be a tight sliding fit. So we picked this. It's not a standard hole pin fit, but it works very, very well for this part. So this one was based on experience. So now we've got everything about this hole and where they're located and how they have to line up geometrically. Let's come take a look over here. So these are the general notes. Okay, this thing here has some special machining operations, and the zone is from the outside in 3 inches. And there's going to be some work done on here. Remember, it was 1 on the other one up above. But now we're saying, oops, and guess what? I want you to set it on here and make this parallel. Very, very critical that these two surfaces are parallel to each other. And that's the parallel sign. So that's about the clapper and the views that are laid out. Let's now take a look at a drawing in general. This is a D-size drawing because there's a lot of stuff on it. And there are some parts to it. There's a title block that says who drew it, when it was drew, what the company is. In this case, we're using ARC Design 330. What the title of this is. This is the clapper. It's for the 4-inch first and second check valve. And this is the machined drawing. And so I gave it a drawing number. The primary scale is 1:1. So if it does not say what the scale is, it's 1:1 on the sheet. Other ones might say something different. This is 2:1 as an example. I've only have one sheet. I'm at revision A. Okay, and we're not doing the QA/MF manufacturing and engineer and approval engineer. We're just doing this. So this is the title block right here. And then there's a make from block. This has to be made from something, and the machinist has to know what to make it from. So there's usually a note or a block that says what to make it from. And so the material is EPDM on GTX. I'm going to just go grab one of these pre-made blanks that was called C4 vulcanized part. I'm going to go grab one of those parts and I'm going to machine it. So it's really important to have the make from. What would happen if I tried to make this part and nobody had bothered to buy these? Well, of course, I couldn't make it. Okay, and this drawing is predicated on this part being done right and all the dimensions from that part being made. Now, remember I said that every dimension has to have a tolerance. It is an ANSI standard requirement, every dimension. But we don't always want to write it down. So if we use 2 decimal places, we'll say the standard tolerance is plus or minus 0.03. So if my dimension was 1.00, I could add 0.03. And if I measured anything between 1 and 1.03, I'd say my part was good. That's my plus tolerance. My minus tolerance is if I took 1 and subtracted 0.03, 0.97. So if I measured between 1 and 0.97, it would also be good. So that's how you read these. Okay, if I was a fractional, I'd go to 1/32. Angular, I can do plus or minus half a degree. And surface finish, we're not really going to talk about. 125 RMS is how big the bumps are that are allowed on the surface. And we might talk about it a little bit, but not much. So these are your standard tolerances. So there's a title block, a make from block, a standard tolerance block, and then something has to tell us when we make a revision. So right now we're on revision A, which is a new release. There have been no changes. And I've made it, so I put the date in here, and I did my own approval. We're going to let you do that. Usually there's an engineering manager or a product manager that makes those approvals. Now this zone is, if I make a change, I don't want to look around the whole drawing. I want to know where to look. So if it was over here, let's say I did it in this view, that's in zone D5. So if I were to make a change, I would note where the person should look to go see what the changed dimension is. So that's your revision history. And then the last thing are notes. Okay, we always have some general notes, and you're just going to copy these down. But in this case, there's a machining note of what to do. I'm going to freeze the part and then machine this zone. And then I'm going to flip it around and I'm going to hold the part against that and this. And I'm going to put these other holes in. And I'm going to put this feature in over here too. Okay. And then, this says, oh, no petroleum-based fluids because of the EPDM. First and last parts get inspected, plus 1 out of every 100 parts. Unspecified radius is 0.03. And clean it using a non-abrasive, non-petroleum cleaning method. So that gives you all of these parts, and it tells you about that. So that's your machining. And let's look one last time, one little bit more, about what's important about this blank clapper. So you'll see many of the same things in here. We have different views. Here's a breakout view. This is an internal part, this depth. And according to ANSI standards, you must dimension to a visible part line, a visible feature. And so I have to do something called a breakout back to this part to make it look. It says, okay, just break this out. I can tell I'm looking at this over here so that I can put this dimension on it. I can put a breakout in here. Okay, this is just saying this is the GTX injection molded part, and this is the vulcanized EPDM. Just giving directions to the person. Here's some basic dimensions. Again, 2 times means you see it in 2 places. So it's 0.245 between this wall and this wall. And so since it's 2 times, it says I mean it over here also. Okay, so when you see 2 times, that means 2 places. And this flat area here, that's just a byproduct of a dimension that's given. Okay, so that's a dimension that's given over to here. I thought I had it. Oh, it looks like I need that dimension on here too. See, there's always something to figure out. You guys know how to do all this, 3 decimal places. And I'm going to leave it as symmetric. And I believe that was a very tight tolerance, plus or minus 5 thousandths of an inch. There we go. Off of the main center line of this. Now I've got that one in there too. So section views. If I cut this section, that's what I would see. And that tells you where the center of this little radius goes. And then it's straight up from there. This is just a cutout that gets made for clearance to another part. So we make this, and then we cut this rectangular hole, and it cuts this depth. So I think that gives you most of everything else that you need to be able to see. So this is for this counterbore here. And this is for this middle one. So this one, as you can see, we see over to there. Oh, there it was. I already had it. See, I already did have it in there. I didn't trust myself. Okay. And the same thing goes on this one. I've got some views. I've got a title block, a make from, standard tolerance block, general notes, all of the general parts that are required. This one's interesting because I have two pieces. I have neural GTX and I have EPDM, and this should be capitalized. We generally write with capitals when we're doing mechanical drawings. Okay, so there's a sort of a review about what goes on with the clapper, and it should help you now as you go about making your parts.